Hello again, class. Today we're going to spend one more day in lesson 9.1. The last lesson we were converting rectangular coordinates to polar coordinates and vice versa. And today we're going to be converting rectangular equations to polar equations and the other direction. For starters, let's just kind of remind ourselves what rectangular equations are. So rectangular coordinates and rectangular equations of what we've been studying over the last several years. So when I think of rectangular, think of x's and y's. And so here are some familiar rectangular equations. So like y equals 3x minus 2, that's the graph of a line. 3x plus 5y equals 10 is another line. We also have circles, x squared plus y squared equals 9 is the graph of a circle. Parabolas, y equals x squared plus 5, or even the polynomial functions that we studied back in the first semester. So again, anytime you're thinking about rectangular equations, be thinking of x's and y's. When we're thinking of polar equations, we haven't actually looked at polar equations yet. We've looked at polar coordinates. And so with polar coordinates, we are looking at r's and thetas. And so we can expect r's and thetas to show up in those equations. Some things that could be helpful to us as we move forward. We looked at these equations last lesson. Let me remind you of those as we will use these again today to help us out. So we have x equals r cosine theta. We have y equals r sine theta. And we also looked at r squared equals x squared plus y squared. That's just the Pythagorean relationship. Or if we would rather use, we can use r equals square root of x squared plus y squared. So let's go ahead and start with a few examples changing rectangular to polar equation. And we're going to start with an easy one. This one, x equals -2. Normally, we would know this as a vertical line at x equals -2. And so, again, if we kind of look at our choices here, some things that we can use to help us out, we see that x equals r cosine theta. So when we're doing this problem, we could simply replace x with r cosine theta. So then we can now say r cosine theta equals -2. And we're done. Simple as that. We now recognize this is a polar equation because, again, instead of x's or y's, we have r's and thetas. Here's another example. This one's a little bit more involved. We have 5x squared equals 3 minus 5y squared. So on this one, again, if I kind of just look back at my choices here, I see, does anything stick out to me? And I notice on this example, there's an x squared and a y squared. And one of my choices suggests that that is equal to r squared. And so I'm kind of thinking if maybe we could rearrange this equation so that we can get x squared plus y squared together. So my first thought is, why don't we move the 5y squared term over to the left side? So now we have this is equal to 3. And then the next thing I might do is factor out the 5. So now I have 5 times the quantity, x squared plus y squared. Oops. And then that equals 3. And then now we're ready to use that substitution. So again, r squared equals x squared plus y squared. And so that means since I have an x squared plus y squared, I can just replace that with r squared. So now I can say 5r squared equals 3. And then there's going to be kind of an ongoing debate throughout this assignment is, how do I know when to stop? Should I simplify? Should I keep going? This is probably one of those cases where, if you stopped right now, it wouldn't be wrong, like to say that this is a polar equation, right? X and Y are gone, we have R instead. I think if you look at examples in the book, you might see that in a case like this, they would probably go ahead and divide the 5 over and say something like r squared equals 5/3. And in our next lesson, when we get this equation, we're going to recognize this as a circle. Okay, right now we're not quite ready to see that yet. If you go back to the original equation, you can see this is a circle. If you divide both sides If you look at this step here, if you divide both sides by 5, you get x squared plus y squared equals 3/5, and that should be an equation that we recognize as a circle. And so later on, when we get to r squared equals 5/3, you could even debate, like, should I root both sides? Should I say r equals the square root of 5/3? It wouldn't be wrong to do that, but I think on a problem like this, I probably would divide the 5 over and then just leave it like this. And we can discuss what this is in particular more in the next lesson. All right, here's one more example. We want to change this to polar coordinates again. This time I see 4xy equals 9. So if we go back to our choices, we see x is r cosine theta, y is r sine theta. So I think I'm going to start there. I'm going to plug those in. So I have 4 times r cosine theta for x. And then I'm going to multiply that by r sine theta for y. And then all of that's still equal to 9. And then I'm just going to do a little bit of simplifying. R times r we could put together as perhaps 4r squared cosine theta sine theta. And all of that will still be equal to 9. And then again, we kind of get back to that debate, is this okay? Am I done? Do I need to do anything further? I think you could make the argument that this is fine and we're done. Again, the main goal is to make our x's and y's go away and have it be replaced with r's and thetas, and we've certainly done that. So we could do that. If you look in the book, you'll notice sometimes they tend to simplify things more, and sometimes they don't. There is something I could do here that might be a little bit hidden and maybe not super obvious, something we studied back in chapter 7. One thing we could do is this 4 here can be broken into factors of 2 times 2. And so what I'm going to do is I'm going to write that as, I'm going to put one of those 2's out front. I'm going to say 2r squared. And then I'm going to bring the other 2 after that, and you'll see why here in just a second. So now I have 2r squared and then 2 cosine theta sine theta. And then maybe you're starting to recognize or something's kind of coming back to your mind. Maybe this looks familiar to you, 2 cosine theta sine theta. You might remember from our list of identities back in chapter 7. Remember our, 29 identities that we looked at? That one of those was a double angle identity that said that 2 cosine theta sine theta was equal to sine 2 theta. And so if we wanted to get a little fancy here, we could argue that it would be simpler to maybe express our answer that way. Now we could say 2r squared is still part of our answer, times, instead of 2 cosine sine, we could say sine 2 theta, and then set that equal to 9. So again, you might be kind of wondering, like, do I have to do that? Would it be okay if I just went back and left my answer like this? I don't think it's wrong. Like the book doesn't really give any specific instructions on when to simplify and how much you could simplify, but I did notice in some of their examples and some of the answers that they provided, they did some things like this. And so if you look at the answers I provide you, you might notice a couple of them I give you 2 choices. So like on a problem like this, I might say this is the answer or this is the answer. At this point in time, I think it's okay either one. If you just leave it like this, that's okay. If you recognize there's something maybe you can do to make it look a little simpler, you certainly could go ahead and maybe give an answer like this. Try not to get overly concerned about whether you do that extra step or not, or you might see that on your answer, maybe you divided the 2 and put it over here, and for my answer I just left it over there. Again, that's not really one of our overarching concerns right now. We can worry about those kinds of things later when we actually start graphing these equations in the next lesson. But for now, again, the main goal is just to replace our x and y's with r's and thetas. And if you're doing that, I think that's going to put you in a pretty good place. So the second part of our lesson, we're going to be doing the opposite. We're going to convert polar equations to rectangular equations. And our book offers 2 strategies that can help with that. One strategy that they suggest is multiplying both sides by r could be really helpful. Or the second strategy is considering squaring both sides. That's another thing that we could do that could kind of help us get things started. So let's run through a few examples of these. We'll kind of start with an easy one again. So I have r equals 8, and if we think about our two strategies, what I usually do is kind of maybe project in my head before I write anything. Think about, well, what would happen if I multiplied both sides by r, or what would happen if I squared both sides? Well, if I multiply both sides by r, I get r squared equals 8r. If I square both sides, I get r squared equals 64. I feel like the r squared equals 64 choice might be a little bit simpler. I don't think the other choice is wrong necessarily, but again, if we kind of go back and look at this table here, we can use these to help us out. So if I have an r squared, I can substitute x squared plus y squared, which is going to be really helpful. If I multiply both sides by r on that one, you're going to have this on one side, and then you're going to have this on the other side. And again, I think that kind of makes things look a little bit more complicated than simply having a 64. And so my suggestion on this one would be to go ahead and just square both sides. I like that idea. And if we square both sides, we'll get r squared equals 64. And then we can simply replace r squared, substitute x squared plus y squared in for r squared. And so then I get x squared plus y squared equals 64. And I think that could be an answer that we're happy with. So notice that r is now replaced, and we no longer have an r, and instead we have x's and y's, and that's good. That's what we want in order to be rectangular coordinates, or rectangular equations. Sorry, that's what this should read up here. Rectangular equations. We now have x's and y's, which is what we want. You might also be looking at this, recognizing, hey, this looks like a circle. I think we maybe kind of saw the opposite of this in one of our last examples, converting the other direction. And so if you recognize as a circle, that's great. And hopefully you start kind of noticing things like that as you do some of the problems. There might be some that you don't recognize, and that's okay too. It could just be some random polynomial equation that isn't overly special to us. And if that's the case, that's all right. Okay, here's another one. R equals 6 cosine theta. So again, our choices here are to either consider squaring both sides or multiplying both sides by r. Again, maybe just kind of play out those choices in your head to see what that might look like. If I square both sides, I'll get r squared over here, which could be really helpful. But over here, I might get like 36 cosine squared theta. And if you go back to our table again, cosine squared theta doesn't really show up on here. So I'm not sure that one's going to be quite as helpful. So instead, if I multiply both sides by r, I'm kind of thinking that might be the choice here, because I'll get r squared still, which is still helpful. And on the other side, I'll get 6 cosine r, or 6r cosine theta. And so let's do that and see how that plays out. I get r squared, and then if I multiply the right side here by r, I could really put that r wherever I want. So I think I'm going to do maybe 6 times r cosine theta. And that's really helpful because we know r cosine theta is equal to x. So now I can replace r squared with x squared plus y squared. And on the right side, I can replace r cosine theta with 6x. So again, back to that debate, like, okay, I've replaced r and theta with x's and y's. That's great. Is this okay for an answer? I think it is. It could certainly be argued that we've accomplished our goal. If you wanted to be a little bit fancy, you might recognize this as in a circle as well. If we wanted to, we could perhaps move the 6x over here and leave the y squared over here. And you might remember way back in chapter 1, we did some completing the square to put our circles into a form where we could recognize the radius in the center. And so you might remember doing that. It looks something like this: x squared minus 6x. So if you take half of the -6 and square it, you get +9. And then whatever we do to one side of the equation, we want to make sure we do to the other side of the equation. And then you could factor, and it looks something like x minus 3 squared plus y squared equals 9. And so again, the debate, which one's better? Is it this one? Can I just leave it like that? Can I leave it like this? I'm okay with either one. If you accomplish your goal and you leave it like this, that's fine. I guess maybe my suggestion would be is if you recognize the equation, you're like, oh, I know this one. This is a circle, or maybe this is a parabola or a line or something, and I can maybe rearrange it into some form that looks a little more familiar. I guess I would maybe encourage you to do that. There's on the answer sheet that I provide, I tried to give multiple answers for a few of them to let you know that both are okay. So again, if you recognize this and you want to do this, great. If it stays like this, I don't think that's the end of the world for today. Okay, here's another one. We have r equals sine theta minus 3. So again, think about, should I multiply both sides by r, square both sides? When I think about squaring both sides, I think about having to FOIL this out, and I feel like that's probably going to get a little bit messy. So I think I'm going to, again, stick with the option of multiplying both sides by r. I think you're going to find yourself maybe taking this option more times than the other option of squaring both sides. Keep them both in mind. They can both be helpful. But I feel like I use this one far more than the other one. So I get r squared equals, and you can say like r times the quantity, or if you want to, I think I'm going to go ahead and distribute that r. So I'm going to say like r sine theta minus 3r. And so the next move I think would maybe to give some substitutions here. So r squared we've used a few times is x squared plus y squared. And then r sine theta, we recognize that as ry. And then, I think we typically prefer if we can turn r into r squared, but sometimes when you're ready to make substitutions, you'll have an r by itself, and that's okay. We can recognize r by itself as the square root of x squared plus y squared. And so I think we have it. We've got, our r's and thetas are gone. Everything's in terms of x and y. When I look at this one, I don't really recognize this as, oh, this is obviously a circle or a parabola or anything like that. So I think, maybe we could leave it like this. I think some examples in the book maybe had a version of an answer where they moved everything over to one side and set it equal to 0. If that looks a little bit cleaner or simpler to you and you want to do something like that, it's not wrong. You certainly can do that. I think both of these equations are equivalent. So I'll kind of leave that up to you as whether you want to just leave it alone up on this step, or if you want to kind of move things over around like this. I think it's okay to do that as well. All right, and this brings us to our last example. I have r equals 2 over 1 plus cosine theta. So again, we start thinking about squaring both sides. I feel like that's going to get pretty messy. You're going to have to FOIL on the denominator. Even multiplying it by r on both sides might get a little bit messy. Like we'll have an r squared over here, we'll have 2r over here. My thought on this one is before I entertain either of those ideas, maybe just go ahead and multiply the 1 plus cosine over to the other side. And when I do that, I get r times the quantity 1 plus cosine theta equals 2. And then if I go ahead and distribute, I get r plus r cosine theta. And I think we might recognize that we don't even have to multiply both sides by r or square both sides. I think this is already in a form where I could go ahead and make those substitutions, and that's going to put me in a good place. For example, we recognize r cosine theta is simply x. R, as we used on the last one, we could say is root x squared plus y squared. So we'll start with that. Root x squared plus y squared plus x equals 2. And then, yeah, I think we've accomplished our goal. If you wanted to, you can maybe move the 2 over and set it equal to 0 like before. This is one, I noticed one of the examples in the book did something like this. They looked at this, and you might recognize this as something that could be cleaned up a little bit. And one way we could do that is maybe move the x over, so I get like 2 minus x on one side. And then, I think I noticed that in the book's examples, they didn't really like having a root in their answer. It's not wrong if you have a root in your answer, but if it's possible to maybe clean that up, it makes the equation look a little bit nicer. So we could do that pretty nicely here, where if we just square both sides, you get x squared plus y squared. And then over here, if you FOIL, you get 4 minus 2x minus 2x, which is minus 4x, and then plus x squared. And then you'll notice like the x squareds actually could cancel out, and then we end up with something like y squared equals 4 minus 4x, or negative 4x plus 4. And so, you know, it's certainly debatable, like, is this simpler or nicer looking than what we had before up here? You know, I think maybe a little bit you could argue that. I think when we look at this, like, to me, I see a parabola sticks out to me because one of the terms is squared and the x term is not. And so that lets me know that this is going to be some sort of parabola. And so, again, it's not wrong if you just left your answer like this one up here. But I noticed maybe the book did something like this, where they were able to get rid of that square root. Now, I go back to this one, you might wonder, well, could I do the same thing over here? I guess we could try, but I think in order to do that, we'd have to move this y over here and then maybe divide the 3 and then square both sides, and then you're squaring something over here with 3 terms, and that's certainly not going to be fun and maybe not give a nicer answer. And so, again, that could be kind of a part of a frustrating part of this assignment, is just knowing when do I keep going, when do I stop. So I think if you don't let yourself get frustrated by that, I think, you know, as long as you have all the right terms and everything's whether they're on one side or the other or whatever, I think it's going to be okay. And I tried to give you a few choices when you're checking your answers today. So yeah, good luck with that. If you have any specific questions, let me know. And we're going to look more specifically at what these polar equations look like and what their graphs look like in the next lesson. So good luck. Sorry, before I wish you off, I probably should show you the homework. I know it's posted in the Google Classroom. But here it is. It's, sorry, I just made a quick change there. It should be page 585, and I'd like you to do 69 through 84, and I'd like you to go ahead and do all of those. So that's a little bit smaller set than yesterday's, and so instead of doing the evens, I'd like you to go ahead and do all of them. And I've provided all the answers in the Google Classroom, so you can check them as you go or when you're done, kind of see how things are going. So good luck.